Hey everybody, welcome back to Astronomy. Let me close my door for a second. So I've apologized for this a couple of times already by email. I don't know what happened to all of my videos from this week. I think what happened, and I'm not going to bore you guys with all the technical details, but I don't use PowerPoint. I use Apple's Keynote, and I had like 5, 6, 7 keynotes open at the same time. And I think what was going on was that one of them had a pop-up and that I never dismissed, and that pop-up was keeping it from communicating properly with Zoom. So the lectures were fine on my screen. Like I saw all the images change over the course of the lecture. I don't know why it didn't go through to the Zoom. I think because of the pop-up, the pause share button on Zoom was kind of permanently depressed, and I didn't notice it or whatever. I don't know. So I'm not recording 5 lectures over again. So what I did was I posted to Canvas, to the pages section, where there's that big table that hopefully you've been looking at every few days to see what parts of the book you should read and stuff like that. I entered in those days this week a replacement video. That is my lecture from last year. So I might occasionally say things about what we did last and what we are doing next, and due dates of stuff that are all wrong because it's from last semester's class. So don't pay any attention to that kind of stuff. But if you were behind on the lectures anyway, watch those replacement videos for this week. I actually deleted all the ones from Zoom. Well, I unpublished them, at least temporarily. I might republish them. But if you already watched the broken videos and you just stared at the same picture for half an hour. By the way, if you think there's a problem with the videos, send me an email. Sometimes things get messed up. The fact that nobody emailed me about the fact that the past 4 videos were messed up makes me worry that maybe everyone is 4 videos behind, which I hope is not true, but never know. That's the problem with these online classes. Anyway, so if you already watched the messed up videos, you don't have to go watch the whole replacement videos, but go open them up and at least skim through them so you can see all the beautiful pictures that I show during these lectures. Anyway, enough about all that. I want to talk about the sun today, super quick. Because I only want to introduce the sun sort of as an example of a star. And then we want to talk about stars more generally. Here's a picture of the sun. We all know what the sun looks like. It's right up in the sky all the time. We know a few things about the sun. It is very hot and it is very bright. We can't usually see the surface of the sun like this without the aid of special instruments that block out all of that bright light so we don't blind ourselves, or so that we don't destroy our optical instruments. So this is a photograph taken through a filter that only lets through a specific wavelength of light corresponding to hydrogen gas. The sun is, first of all, big. Here is the sun to scale with Jupiter and Saturn and the Earth and Moon. It is more than 100 times wider than the moon. And since the volume of something goes like the cube of its size, you could fit more than 1 million Earths inside of the sun. The sun has by far most of the mass in the solar system, more than 99% of the mass of the solar system. All the planets, all the comets and asteroids, all the junk out in the Kuiper Belt adds up to only 1% of the mass of the sun. The sun rotates on its axis. This was discovered by Galileo. If you remember, we mentioned that one of the things Galileo discovered with his little telescope was sunspots, and they go around as the sun rotates. But the sun is not a solid object, so it doesn't rotate as a solid body. It actually rotates faster at the equator than at the poles. At the equator, the gas there takes about 25 days to go around, and near the poles, it takes more like 28, 29, 30 days to go around. So we've known for quite a while the sun is gaseous, or actually plasma. The gas is ionized, and that it exhibits what we call differential rotation. It doesn't rotate as a rigid body. The different parts actually rotate at different speeds. We also know that the sun is dynamic and constantly changing. We mentioned the fact that Galileo discovered these sunspots on the surface of the sun that not only look different from the rest of the sun, but they change over time. Sunspots appear and disappear. And the sun also has bursts of activity on the surface. We can see on edge these the they call them filaments, these just like lines that crisscross the sun. When you see one of those on the edge of the sun, it's called a prominence. It can actually see this gas arcing off the surface of the sun. And we can see the structure of the sun if we look very, very close. Sunspots are areas of the sun's surface that have a lower temperature than the rest of the surface. The surface temperature of the sun's a little less than 6,000 degrees Kelvin, about 5,500 degrees Celsius. The temperature of a sunspot is only about 3,000 degrees Kelvin. So way cooler, right? About 2,000 degrees Celsius cooler. If you could zoom in on this picture and just look at a sun, or you could take a telescope and zoom in on the sun and just look at a sunspot, it would still blind you to look at a sunspot. They're not black. They're just not as bright as the rest of the sun. So when you filter out 99.9% of the sun's light so that you can look at it like this camera is doing, the sunspot looks black relative to the incredibly bright surface of the sun around it. So the very, very dark appearance is due to the fact that you're filtering out 99% of the light to photograph the sun in the first place. Without getting into loads and loads of detail, what's happening in the sunspot is the magnetic field of the sun is inhibiting the convection of hot plasma from the inside of the sun to the surface of the sun. The sun has a very strong magnetic field. That magnetic field affects the motion of this ionized gas that the sun is made out of. By the way, almost all hydrogen. And the sun is 90% or more hydrogen gas. The universe is more than 90% hydrogen gas. Almost everything is mostly hydrogen gas. This ionized plasma, it can move and flow around, and the sun's magnetic field exerts a force on that ionized plasma and inhibits the flow of heat from the inside to the outside of the sun. Here's a close-up of a sunspot, and those lines that you see are actually trace the sun's magnetic field lines. If you think about, I think they still do experiments like this in middle school. Did you ever do an experiment in middle school where you take a magnet and you put it under a piece of paper and you put iron filings on top of the piece of paper, and the iron filings line themselves up with the magnetic field? That's what's going on here. The flow of ionized plasma at the surface of the sun is flowing along these, it's lining up with the magnetic field lines in the vicinity of the sunspot. You can also see this phenomenon called granulation. The surface of the sun is broke up into these tiny cells, and those cells are the result of convection, which we'll talk about in a minute. Here's a picture of the edge of the sun during a time when it's experiencing a solar prominence. And you can also see that the lines of flow of this eruption of gas from the surface of the sun follow these magnetic field lines. And these prominences are caused by instabilities in the sun's magnetic field. And again, we're going to kind of talk about this stuff in a pretty vague way without getting into the nitty-gritty details of, the dynamics of plasma and a magnetic field. We're not really equipped to do that. I'm not really equipped to do that. Suffice it to say that it's the interaction between the plasma that the sun is made out of and the magnetic field generated by this rotating plasma that's the result of that results in the structures that we see on the surface. Here's Earth 2 scale. One of these solar prominences, a very big solar prominence, sometimes called a solar flare, can actually eject material out of the sun. And this material feeds into the solar wind. A very large magnetic storm on the sun can actually affect communications here on Earth. It can mess with radio signals and stuff. Here's a movie showing one of these eruptions, one of these prominences bursting from the surface of the sun. You can see that the flow of the plasma is always along these magnetic field lines. I think it zooms out in a second. There we go. So you can get a sense of how the scale of that prominence relative to the sun. And you can see some other stuff going on the other side. So the sun is dynamic and active, and its brightness changes slowly over time. We know it was dimmer in the past, and the number of sunspots and the activity of the sun's magnetic field also changes over time. And it's actually periodic. There's a fixed cycle of times when the sun has a lot of sunspots and its surface is very active, and times when the sun has very few sunspots and its surface is very inactive. And then this cycle repeats itself every 11 years or so, and has been doing so ever since we discovered sunspots. This is Galileo right here, 1609. These dots on this graph are Galileo's observations. There was a long kind of quiet period during the late 1600s, but the sun is falling. Notice the peaks aren't always the same height. The maximum activity isn't always the same, but the spacing is always the same. It's always this 11 to 12 year cycle. We are right now at a period of a solar minimum. That means if I took my little telescope that has a solar filter, I went outside right now, I pointed at the sun, I would probably see very few sunspots, maybe one, maybe two, at a time when the sun's at a maximum of its activity, of its magnetic field. I might see dozens or even 100 sunspots through my little telescope. So the sun is somewhat variable in its activity. Its brightness is fairly constant, but there are stars that are not. There are stars that are not only variable in their activity of their magnetic fields or whatever, they're variable in their size and brightness, and the star actually pulsates and gets brighter and dimmer and brighter and dimmer. Those are called variable stars, but our sun is a relatively well-behaved star that only changes on cycles of many, many, many years, and those changes are confined to the activity of the surface, not the brightness of the star as a whole. You don't have to memorize all of these layers and their names and the order and the temperatures, but it is important to know this about the sun. The surface temperature of the sun is a few thousand degrees Celsius, about 6,000 degrees Celsius. If you go deeper, deeper, deeper into the sun, it gets hotter and hotter and hotter and hotter. But also, if you move away from the surface of the sun, it gets hotter. There's a region outside the sun called the corona, the solar corona. This comes from the work for crown, because during a solar eclipse, it looks like spiky crown surrounding the sun. The corona is actually hotter than the surface. So the surface of the sun, the light we see from the sun, comes from the photosphere and the region surrounding that. You can think of the photosphere as that's the place where the gas of the sun goes from being transparent to being opaque. So when we see the sun and see its surface, like the sun's all gas, it doesn't have a solid surface of any sort, but that gas gets denser and denser and denser until you can't see through it anymore. And that's the point we call the photosphere. The atmosphere of transparent gas surrounding that's called the chromosphere. And the thin envelope of gas that extends millions of miles out into space is called the corona. The corona is the part of the sun that you see during a total solar eclipse, when the moon blocks the sun and we can see the light of the sun coming around the moon. That is the light of the corona. The corona of the sun can have temperatures of more than 1,000,000 degrees Celsius, 1,000,000 degrees Kelvin, even as high as 10 million Kelvin. That's weird because the energy of that solar corona has to come from the sun, right? And if the temperature of the sun is only 6,000 degrees Kelvin, how can it heat the corona to millions of degrees Kelvin? That doesn't make any sense. It seems to violate the law of conservation of energy or something. This is a question called the coronal heating problem. Go to Wikipedia, there's lists of unsolved questions in physics and astronomy and various fields. The coronal heating problem is one of the questions on the list of unanswered questions in astronomy. We don't know why the corona is so hot. It almost certainly has something to do with the interaction between the magnetic field of the sun accelerating the particles in the corona faster and faster and faster. And that's what heat is, right? Heat is just molecules and atoms moving real fast. So it's some kind of interaction between the magnetic field of the rotating sun and the material, the corona, but we don't really understand how it works. Do I have a slide in here about the Parker Solar Probe? I do. We have, this is from 2018, the Parker Solar Probe is up there right now, orbiting the sun, getting closer and closer to the sun every year. It's a super complicated orbit. It would be cool to go to the NASA website for the Parker Solar Probe and just look at where it is now and to look at its orbit, because we sent it towards the sun. It flew past Venus a few times. It flew past Mercury a few times. And every time it flies past Mercury or Venus, it nudges it in an orbit that's a little bit closer to the sun. So it's getting closer and closer to the sun as it goes. It's the closest we've ever gotten to the sun. It's passed through some of the hottest parts of the corona. And the job of the Parker Solar Probe is to measure the properties of the corona and try to get a better understanding of the coronal heating and why the corona of the sun is so hot. We've talked a few times when talking about the planets about the solar wind. The solar wind is a stream of charged particles that's released from the upper atmosphere of the sun, from the chromosphere. It's mostly electrons and some protons and some alpha particles. And alpha particles, a helium nucleus. Sometimes I take for granted that people understand some basic chemistry. Hydrogen is 1 proton, 1 electron. It's the simplest element in the periodic table. Right? Helium is 2 protons, 2 neutrons, and 2 electrons. It's the second most simplest element in the periodic table. If you take the electrons away from a helium atom, you have 2 protons and 2 neutrons stuck together. And there's an old-timey name for that thing, and it's called an alpha particle. It's a kind of radioactivity. Well, that's a dumb way to say it. It's a hydrogen nucleus, but it's what's given off in some kinds of radioactivity. Very low level, not particularly dangerous radioactivity. Anyway. What's coming out of the sun's electrons and protons and helium nuclei, and they're accelerated by the sun's magnetic field to very, very high speed. Again, just like we don't understand why the corona of the sun is so hot, we don't entirely understand where all the energy of the particles from the solar wind comes from. Again, it probably has to do with the magnetic field kind of pumping energy into these particles as they flow outward from the sun, but there's still lots of unanswered questions about it. By the way, that's good. Unanswered questions are the way we learn things about science. They're not something we're embarrassed by or ashamed of or like to pretend don't exist. I talk about unanswered questions in this class all the time because unanswered questions are what science runs on. And we talked about the fact that here on Earth, those particles from the solar wind, because they're electrically charged, electrons and protons, they are deflected by the Earth's magnetic field and they tend to wind up hitting the Earth at its poles. And when those charged particles hit the poles, they deposit their energy into the atmosphere, and they can cause the atoms and molecules in the atmosphere to glow. And that is what causes the northern lights and southern lights, the aurora borealis and the aurora australis. The outside of the sun is just hot plasma, hot hydrogen gas. The outer layers of the sun don't make any heat. They're just hot. They're heated by the interior of the sun. We can think of the interior of the sun as split into really 3 zones. The core, which is where the heat of the sun is generated. The radiative zone, where heat moves outward from the core towards the surface. The convective zone, where the material of the sun is actually free to flow and move and carry that heat to the surface, and then what we call the surface, or the photosphere and chromosphere. The way to think about the difference between the radiative zone and the convective zone. Well, first, let's think about gravity and pressure. What holds the sun together is gravity, right? And then gravity is squeezing the sun. All the mass of the sun is squeezing everything to the center. So the deeper you go, the denser and denser and denser and denser it gets. The greater and greater the pressure gets. The pressure gets higher and higher and higher. And the greater and greater and greater the temperature gets. It gets hotter and hotter and hotter as you move towards the core. In the radiative zone, the gas of the sun and the plasma of the sun, and sometimes they use gas and plasma interchangeably, right? Plasma is just a gas where the electrons have been stripped away from the outside of most of the atoms. It's so dense that it can't really move and flow around. It's almost like a solid in that way. The analogy I sometimes, do I not have this analogy? Oh, that's terrible. Sometimes I have a little picture here. That's an analogy for how to think about these layers of the sun. And I think about it in terms of, imagine you put a pot of boiling water on the stove. Okay. You're making spaghetti, you're making macaroni and cheese, whatever. So you've got the stove, you've got the pot, you've got the water. Okay. The stove is like the core of the sun. That's where the heat comes from. That's what's making the heat. The pot doesn't make any heat. It just gets heated up by the stove. The pot doesn't move around and flow. It just gets hot and transmits that heat from the burner to the water. That's like the radiative zone. The radiative zone is just super, super hot. It doesn't flow or move. It just carries heat by conduction, essentially, from the core to the next layer up. But the water in the pot actually flows and moves. You can, when you make a pot of, rice-a-roni or mac and cheese or whatever, and just look at the water, you can see the water moving. You can see it rising and falling. That's actually what makes these shapes on the sun's surface. They're convection cells from the material rising to the surface and then falling back again. You can see these same sorts of convection cells forming in your mac and cheese sometimes when you've got it on the stove burner. In the bubbles, you can see these little hexagonal patterns from the rising and falling of the material. So the water is like the convective zone. The whole material is moving and carrying that heat to the surface and then sinking back down again. Okay, so the core is like the burner. That's where the heat comes from. The pot is like the radiative zone that carries heat from the core upwards without moving, just through convection of heat. And then the conduction of heat. And then the convective zone is like the water in the pot, where the material is actually free to move around. The temperature, as I said, on the surface of the sun's only a few thousand degrees Kelvin, about 6,000 degrees Kelvin, 5,500 Fahrenheit. That's about 10,000, 6,000 Kelvin, about 5,500 Celsius. It's about 10,000, a little more than 10,000 Fahrenheit. The pressure, if you could hover there on the surface of the sun, there's no place to stand, but if you sent a spacecraft to the top of the photosphere, the atmospheric pressure it would feel from the weight of all this gas and the chromosphere pushing down on it would be hundreds of atmospheres. But the core of the sun is where the sun does its thing. It's where the heat of the sun comes from. The temperature there is not just a few thousand degrees, but millions of degrees Kelvin. And the pressure there is not just a few hundred atmospheres. It is billions of atmospheres. It is the weight of the whole sun, which is millions of times bigger than the Earth, gravitationally pushing down on all that hydrogen and helium in the core. That state of affairs is what allows the sun to generate heat. The fact that the temperature is millions of degrees and the pressure is billions of atmospheres. And the process that happens there in the core of the sun is a process called nuclear fusion. Nuclear fusion only happens there in the middle. This part of the sun we see on the surface, there's no nuclear fusion happening there. Okay, it's just heated up from the inside by conduction in the radiative zone and convection in the convective zone. All of the fusion in the sun happens in that little middle 20% or so in the very, very center of the sun. So the sun exists in a state of what we call hydrostatic equilibrium, which is just a big word for a balance between two forces. There are two forces acting on the sun primarily that govern its structure. Gravity is pulling everything in. Gravity is pulling every part of the sun towards every other part of the sun. It wants to crush the sun into a black hole. What keeps that from happening is that the sun is generating heat, and you heat a gas up and it expands, right? If you take a balloon and heat it up, or your tires get a little bit bigger in the summer. If you think in terms of nuclear fusion, the sun's a big hydrogen bomb. It wants to blow up from all that heat. So thermal expansion pushes outward, gravitational attraction pulls inward. And for the past 5 billion years or so, those two forces have been perfectly balanced. Okay? And that's why the sun is the size it is. If it were to cool off, it would start to shrink. If it were to heat up, it would start to expand. But right now, the sun's thermal expansion and gravitational attraction are equally balanced in this state of hydrostatic equilibrium. Next slide. So I said that the sun is made mostly of hydrogen. Hydrogen is just one proton and one electron, and some helium. Helium is 2 protons, 2 neutrons, 2 electrons. So I've drawn protons here as blue balls, and neutrons here as little red balls, and electrons as little glowing spots of light. Don't take any pictures of the insides of atoms seriously. They're just doodles. They're just roadmaps. This is not what atoms look like. They're not little colored balls and little lights zipping around. We talked about that when we talked about spectroscopy. So that's helium. The process that occurs in the core of the sun is fusion of hydrogen into helium. That process is called nuclear fusion. There are other kinds of fusion as well. You can fuse helium into other stuff and whatever. But in the sun, the primary process is the fusion of 4 hydrogens into 1 helium. Now you can look at that picture and see that something doesn't quite add up. Helium's got some neutrons in it, and those hydrogens don't have neutrons in them. Where does that neutron come from? Well, you can kind of think of, look, if a proton is positive and an electron is negative, can you stick them together to make a neutron? Kind of. I mean, like, that's not exactly what's happening, but that's the end result, is that the electron and proton go away and there's a neutron in its place, and the actual process is way more complicated than that. I'm not sure we'll have time to get into the nuts and bolts of the details of that. But suffice it to say that when those 4 hydrogens fuse together, the result is a helium nucleus and 2 electrons, so a helium atom. That process is what we call nuclear fusion. And you can fuse 2 heliums, or I don't know, 2 heliums together into a beryllium. You can fuse 3 heliums together into a carbon. You can fuse 2 carbons together into whatever atomic element 24 is. You can fuse together anything. But nuclear fusion in the sun is hydrogen to helium. I can't believe I just said nuclear a second ago. It's one of my pet peeves. People have pronounced the word nuclear, where the L comes right after the C, as nuclear, where there's another U in there that doesn't really belong. Nuclear fusion. How does nuclear fusion create energy? Nuclear fusion creates energy because if you take the mass of 4 hydrogen atoms and you add it up, you find that that number is actually a little bit more than the mass of 1 helium atom, which means when you fuse 4 hydrogens together into 1 helium, the amount of matter, the amount of mass, is actually a little bit less. You might have learned in chemistry class that that's not allowed, that there's something called the law of conservation of mass that says whatever goes into a chemical reaction, whatever comes out of the chemical reaction, have to have the same mass. That's not true of nuclear processes. In nuclear processes, a little bit of mass can go away, and that mass can be converted into energy. That is the meaning of Albert Einstein's equation, E equals mc squared. It's that mass is itself a type of energy, and you can convert mass into energy in certain processes, largely nuclear processes or processes that involve like matter and antimatter, stuff like that. So in the process of nuclear fusion, we lose a little bit of the mass of those 4 hydrogen atoms, and that mass is converted into energy. And this equation equals mc squared says the energy is equal to the mass times c, which is the speed of light, squared. And the speed of light is a big number, right? Light is fast. 300 million meters per second. So 300 million squared is 9 and then 16 zeros. So even a little bit of mass that gets converted into energy makes a huge amount of energy. This is why nuclear power plants don't need a whole lot of fuel. Well, they use fission and not fusion, but it's the same deal. Mass is being converted into energy. It's why hydrogen bombs can be really, really small, but blow up a whole city, because they're converting a tiny bit of mass into a huge amount of energy. So the process that fuels the sun is the conversion of hydrogen into helium by nuclear fusion. That converts a little bit of the sun's mass to energy. A lecture I sometimes do around this part of the semester, I'm not going to do it for you guys because we're so short on time, is to do a calculation of how much hydrogen has to be converted into helium in the sun every second, and to calculate how long the sun can keep doing that. When you do that, you find, yeah, it has to be a lot of hydrogen converted into helium every second, but the sun's super big and it can keep doing that for billions of years until it runs out. It's worth mentioning here that nobody understood. Oh, I just said that we're going to do this. We're not going to do this calculation. It's worth mentioning that nobody understood what makes the sun hot until the earliest part of the 20th century. Albert Einstein's equation equals mc squared isn't invented, discovered, however you want to think about it, until 1905. Arthur Eddington does not piece together the idea of converting mass into energy through fusion of hydrogen and helium until the 1920s, mid-1920s. What did people think heated the sun before this? They thought it was just gravity compressing the sun and heating it up. Just like if you take a bicycle pump and you hold the tube of the bicycle pump and you push down on the plunger really hard, you can feel it heat up. When you compress a gas, it heats up. So they thought, well, gravity is just squeezing the sun and that heats it up. But that has limits, right? You can't just squeeze the sun forever. There wouldn't be any sun. It would have disappeared. If you calculate how long that process can last, it's not very long. So it was kind of an unanswered question in the beginning of the 20th century. Where does the heat of the sun come from? It can't be burning, by the way. The sun can't be on fire, like a big lump of coal with an oxygen atmosphere that's just on fire. If you calculate how much energy burning makes, the sun would burn itself out in 10,000 years. Like there's nothing that burning gives off so little, and the chemical reaction of burning gives off so little energy that the sun would have to burn itself completely out in a few thousand years to give off as much heat as the sun gives off. So it couldn't be burning. It's probably not just thermal compression of gas, but it wasn't until the 1920s that we got a handle on this. There's if you have HBO Max, there's a documentary, that's documentary, what would we call it? A biopic, I guess, of Arthur Eddington, the guy who discovered this. Is called Einstein and Eddington. It stars David Tennant as Eddington and Andy Serkis as Albert Einstein. So if you are either a Doctor Who or Lord of the Rings fan, there's something there for everybody. I watched it. I don't remember it being great. But what fascinates me is the fact that, like, my grandmother was alive and we didn't know how the sun worked, like the 1920s. That's crazy to me that in the first quarter of the 20th century, people had no idea what made the sun hot. That I find remarkable, just from a historical standpoint. That's something that basic we hadn't figured out yet until the 1920s. So that's what I'm going to say about the sun for right now. Normally, if we had a few extra weeks, I would spend a little more time talking about the nitty-gritty nuts and bolts mathematics of nuclear fusion. I don't think we're going to have time for that. I think what we'll do instead is take a look at other stars, how they are similar to and different from the sun, and how the life cycle of a star is related to the process of nuclear fusion and the availability of hydrogen fuel for nuclear fusion and what happens when that starts to run out. Okay, so I think that's where we're headed next. So that's all we'll say about the sun for now. As always, I will give you a little supplemental YouTube video to watch. I'll give you some sections from the book to read. But we are ready. It's Friday now. We're ready next week. We've got to get on to talk about stars and stellar evolution so we can get to the good stuff by the end.